Okay, good morning. My name is Harry Ricker. This is the Cosmology Discussion Group meeting for March 1. We're into the springtime here. Yay. The cold weather has left us for a moment or two. It was a brutal winter here, believe me. Okay, let's see. Jim was going to talk to us. I don't see Jim. I don't see Jim.
No, he's not here yet.
So Jim was going to give us a talk about, I guess he's been doing work on Nobel Prizes and how long the work of a Nobel Prize physicist survives before somebody discovers it was wrong, which I think is kind of an interesting topic. But if he doesn't show up, I guess we're not going to hear about it.
Would
I
you
like
like
the
to
topic.
spend a minute or so just giving me some responses to yesterday's talk? If I don't know if you were there, but Musa's talk. Do you hear that? Or
Um, you want my opinions or do you want
yes,
other
yes.
people's opinions? You want
No,
my
I hear
opinion?
you. Yes.
I
What?
figured you were going to ask me this, and I'm hesitant to say this, but I don't think that you should pay attention to people like Kev who throw bombs into the presentation from the weeds. He's hiding in the chat. If he's going to say something, he should come forward into the green room and reveal himself and not just throw bombs into the chat, which
Get
he's
some
been doing.
cojones.
Yeah,
Sorry, what
I
was
don't think it does us any good to have a presenter give a presentation and then basically point out what the presenter said was wrong. I just don't see that as being a very good policy. Does that help you,
it helps me. I mean, I think it's probably true to say that I'm very facilitating to any comments, including Kev's, which are basically, the
Yeah,
mainstream.
but if you're going to make a comment like this is wrong or blah blah blah, I mean, you need to back it up, and you can't do that from a chat. And I just think it's disrespectful to a presenter, frankly.
Okay, well, thank you for that. By the way, I think though the audience can make up their own minds about that, and I think Musa.
Well, I'm not. I just don't think that. I think it makes the presenter look foolish, and
Yeah,
he's not really.
I think Musa is mature enough and strong enough to withstand that.
Well, but there's the
But I
other
take your
side of
point.
the coin, which is a guy can bring up something that the presenter doesn't know anything about. What about this? Explain this. How do you explain this? And the presenter sort of law. Anyway, you asked me and I gave you my answer.
Okay, well, thank you. I don't want to take up more of the time
All
for
right,
today.
so Jim's here now, so I guess we can start with the presentation.
Thank you. Hello. Sorry if
Morning,
I was
Jim.
late. Okay, here's an analysis I did on physics Nobel Prize lifetimes. In other words, it may be that certain Nobel Prizes actually decay and expire with time. I got interested in taking a look at this because Nobel Prizes had been mentioned several times in these discussions over recent months. And so here we go. As an abstract introduction, Nobel Prizes in physics may have a limited lifetime. Awarded theoretical work may become subject to widespread, well-founded critique, and specific theories may be outright ruled out or eliminated by subsequent studies. Methodological advances, awarded prizes, may become outdated or surpassed by later advances, increasing spatial or temporal resolution in experimental situations, for example. as well as observational studies. In this pilot study, mean and median selected physics Nobel Prize lifetimes were found to be 51 and 59 years, respectively. So here we have figure 1. Selected physics Nobel Prize lifetimes. On the left here, we'll come back to this. Each line here is a whole story in itself. Let's explain this. Methods and results. All Nobel Prizes in physics were obtained. That's N equals 144 Nobel Prizes from the Nobel Prize Committee website itself. Among many possible sources, the Journal of Binary Mechanics was used to identify decayed or expired physics prizes according to the criteria described above. N equals 28. So there's 28 lines here. There could be more with further analysis of among these 144 prizes. And these are listed in figure 1 by year, recipient, and topic. So let's take a look here. For example, in 1929, we have de Broglie. The topic was his wave nature of electrons. And those are the 3 items then listed for that prize as they're listed in table 1. Note that the work, the topic, was done by recipients before prize year. That's on figure 1 on the left here, the prize year. Obviously, the prize is given for work done previously, and so I'm just pointing that out before the prize year. The first of possible multiple recipients is listed, and brief topic description are visible in figure 1. In many cases, there's only one recipient, like in 2020, Roger Penrose, or there might be multiple recipients in a given year, and not all of the names are visible in table 1. Thus, the lifetime of 19.4% of physics Nobel Prizes was limited according to this analysis. For each Nobel Prize, a Journal of Binary Mechanics paper and its publication year represent one or more publications pertinent to determining prize lifetime in years. So here we go back to table 1. We have the paper where most of the title of the paper is visible. For example, Quantum Technology Advance, bringing into question Max Born's work on research in quantum mechanics. And the paper here was in 2025. As the text below is going to say, we can then subtract 2025, as shown here, minus 1957, or let's say 1954 for the Max Born item. And so the lifetime then we have for the Nobel Prize is 71 years. What did I do? Oh, I went to the nuts. How do I get out of this? I went to the, gee whiz.
Well, we see the chart.
Yeah, I clicked
in,
on the picture, and
you're in
There's a restat at the top left, perhaps.
slideshow, I think.
oh yeah, the X.
No. Well, okay.
Thank you, Ian. I got lost there. This technology is something. Oh, okay. So for each Nobel Prize, a paper was chosen as I have described. Lifetime varied from 96 years to -7 years. Okay, we'll look at that now in more detail. The two cases of negative lifetime indicate the Nobel Prize was actually awarded after its own expiration, according to the present analysis. So let's see here if we go up. I'm using the arrow keys. The mouse is not moving this. Okay, let's see. Good grief. Oh, okay, excuse me, gentlemen. You can see here the last two items actually have a negative lifetime. In other words, Rainer Weiss and company was awarded a Nobel Prize for the LIGO gravitational waves after 1 year after the publication in 2016, which debunked that work. Which you know, so that's the explanation for the negative times there. So let's move on down. So for each Nobel Prize, a paper representing one or more publications. In other words, the table lists only one publication, but there could be one or more publications pertinent to determining prize lifetime in years, which is, as I was trying to explain, equal to the year of publication minus the year of the prize award. Lifetime varied from 96 years to -7 years. The two cases of negative lifetime indicate the prize was awarded after its own expiration. The mean and median lifetime was 51 years and 59 years, respectively. Let's see if I can scroll down here. Okay, selected lifetimes ordered by year. Figure 2 shows declining lifetimes for the prizes selected in Figure 1. These declines are grouped in 4 steps. 1, 2, these are for the oldest times, 3, and then finally 4 here. So there seem to be 4 periods in the Nobel Prize Committee in terms of the lifetimes of the awards that they did grant. Discussion. The data presented suggests that the Nobel Prize Committee has done well in selecting award recipients and topics over a 144-year history. This conclusion is not diminished by selection of 28 decayed or expired prizes, since future developments in physics could not be known at the time of these awards, or those awards. Indeed, a robust 80.5% of the awards remain, according to present results. This favorable, I might expire myself during this talk.
Let's hope not.
Yes, I agree with that. This favorable outcome also reflects well for the physics community making nominations for the Nobel Prizes. The 4 steps in decayed prize lifetimes, Figure 2, may reflect some changes in committee composition, protocols, priorities, etc. However, the declining lifetime trend might indicate increasing difficulty in identifying and awarding work of enduring scientific merit. Methodology. A potential weakness in the present methods. This is one thing that good research papers include, if I may say so. What the weaknesses are in the methods that they themselves use. And oftentimes in presentations here, we don't hear anything about that. That should be included in presentations as much as possible to make them more credible. A potential weakness in the present methods is use of the author's publications in the Journal of Binary Mechanics. On the other hand, these papers provide unique source information based on study of the full quantization axioms of binary mechanics, not easily found elsewhere. Further, pursuit of the consequences of these axioms has produced noteworthy discoveries, including the proton and electron cycles, the Keene law of motion, the Keene scale, which replaces the Planck scale, and the derivation of the measured values of so-called fundamental constants from first principles alone. Another weakness may be bias of the author, myself. This bias issue may be addressed by applying the rule, authors write, but readers decide. Okay, new questions. The results suggest further questions. To what extent may these results for physics apply to other Nobel Prize categories, in chemistry, in peace or whatever? Do the 51-year mean lifetime and 59-year median lifetime imply that it takes about 2 generations in years for the physics community to catch up with current discoveries? Do the 2 negative lifetimes, figure 1 lower, indicate that the Nobel Prize committee and those making nominations for prizes are themselves less informed of recent discoveries and advances in physics in more recent years? And what is this? An appendix. Oh my gosh, I thought we were done. Let's see here. The appendix. Figure 3 lists selected physics Nobel Prizes consistent with or further confirmed by subsequent work in binary mechanics. So we're not all negative here, okay? Figure 3, Nobel Prizes confirmed by binary mechanics. The layout of the table is the same. Millikan's work is confirmed. Niels Bohr, his prize, Wolfgang Pauli. These are just some of the names that I myself recognize right off the bat. Okay. Let's scroll. Let's see if I can scroll down without destroying the whole. Additional analysis might add other prizes to either figures 1 or 3. Each row of figures 1 and 3 represents a separate story in advances in physics. Now, if we go back up to table 1, we have here some famous names that their prizes have expired, like Heisenberg, de Broglie, Schrodinger, Planck, Albert Einstein. For what? What did he do? Theoretical physics. Well, he's been excluded. Not only has his work been questions and subject to certain critique, but it's been actually eliminated or excluded by observation. So it's off the table. So each line here in these tables is a whole story in itself, okay? And that might be subject to some discussion, like we see Roger Penrose down here. I guess I mentioned that. Like binary mechanics cosmology, definitely substantially updated and ruled out a number of the features.
Jim, your volume has gone down significantly.
Okay, let's see. Can you hear me now?
That's better. Did you increase the volume or?
Well, I know I just lifted my head a little bit so that I'm talking more into the mic.
Okay,
And,
try that.
okay, now that sort of ends my official presentation. So thank you for the forum, and any discussion I'd be happy to entertain.
I like it, James. It shows that you need to, that biases that come into presentations need to be pointed out, and the fact that almost 20% of not patents, no, prizes are found out to be false.
Well, I don't know whether I go so far as to say that they're actually false, because at the time it may have appeared that these particular authors, like Heisenberg, Schrodinger, and so forth, Otto Stern with the up and down spin work, and so forth, all appeared to be very interesting. Like we have down here in 1949, Yukawa with his nuclear forces and all of that, which binary mechanics definitely modifies and really sort of eliminates. So the as I say, each line of this table has its own story and its own documentation, and whether or not those Nobel Prizes should have been awarded at the time, I'm not really saying that they should not have been awarded, or that it was a mistake to award them. I'm just saying that they appear to have a limited lifetime according to some fairly reliable criteria.
Well, it's all mostly all based on theory and observation of experiments. Some of it's not, but and then once that theory, someone else grabs a hold of it and tears it apart and looks at the pieces of it and can show that with maybe new technology that's come along, that or finer detail or resolution, and they can see that it's wrong, and they write a paper about it and prove it wrong. That's the way I see it. I mean, that's the way things, paradigm shifts happen.
With regard to the Einstein Prize, it's frequently cited that he won it for the discovery of the photoelectric effect. That's actually not quite correct. As you say here, he won it for his work in theoretical physics, and it did append to that, particularly his discovery of the photoelectric effect. Relativity wasn't mentioned, that is true. So one might have to define in a bit more detail which elements you're talking about. I mean, you seem to be talking about the gravitational aspects, maybe of GRT.
Citing his paper in which he says that the advance or the Nobel Prize is superseded by the binary mechanics result. Did I say that correctly, Jim? I'm not sure. I think where you say gravity increased by lunar surface, you're referring to the binary mechanics paper where you show that this was superseded by binary mechanics. Is that correct?
Yeah, right. The surface temperature, it was more important than the total energy of the moon.
Yeah, so in other words, the criterion for the supersession of the prize is a paper in binary mechanics. So
Exactly.
yeah, so obviously a lot of people will have different criteria. In particular, they would disagree with some of your figures or
Quite,
ideas.
quite true. Yes, I addressed that in the discussion.
Well, I think Jim is pointing out where his theory and his work in binary mechanics has obviated a Nobel Prize conclusion or a Nobel Prize work. You've superseded it, maybe would be a better word.
Supersede sounds good. Yeah. One could say that the right side of the table, with starting with the Journal of Binary Mechanics paper, column is superseding what came on the left, or just updating it, or and therefore conclude that there's been some decay in the Nobel Prizes listed on the left.
See, I mentioned the Einstein business because it's a bit unclear because there's so many aspects. As I say, you're talking about the gravitational aspect here, but I could say that it was it's a negative value there actually because it was superseded in 1913. The basic ideas of special relativity were superseded by the Sagnac work in 1913. So I'd have to subtract. 1921.
You
What is
bring
that?
in that's another controversy.
Eight years.
I
Yeah.
don't think Jim's addressed that in his paper here.
Well, actually, though, um, to applaud Ian here, I think he's pointed out that yes, these prizes can be analyzed from many points of view, and I find it rather interesting that he's moving the Einstein Prize in 1921 down to the negative lifetime category based upon other criteria, which are as valid as those that I presented with regard to the Journal of Binary Mechanics papers in his mention of Sagnac experiments. So that one of the reasons I decided to publish this little analysis after I got interested in it and started to look into what the prizes were. And by the way, there's 80% of the prizes are not listed in table 1. And so there's more analysis to be done. But I picked out the ones that seem to be most prominent and easier to determine what their lifetime was. So thanks, Ian, for that comment. I think is very appropriate.
Thank you, Jim.
Okay, well, any other comments? I did want to point out that your second table, if we could go down to the second table.
Yeah, I added the second table just to show that it's not all negative in my mind, that there's the work, at least in binary mechanics, has actually confirmed many of these results.
Oh, okay. So this table here is confirmed by Bernier. Now, I don't understand how Peebles, cosmology, and I noticed that there seems to be 1, 2, 3, 4 cosmology references.
Yeah, correct.
So you're saying that's correct, or you're saying that binary mechanics confirms those cosmology conclusions?
Well, at first glance, now I may have made a mistake in putting this into the into this table, but that's
so
what
I'm wondering. I'm going to wonder right off the bat is I don't know whether there have been any Nobel Prizes given for discovery of dark matter, or I think maybe somebody got a prize for discovering dark energy. I'm not real sure about that. But that would be kind of controversial in my mind.
Yeah, well, I haven't listed all of the prizes that were not in tables figure 1 and figure 3, which would be what, about 100 or 90 other prizes. So that if we were to scroll down that list, I have it in an Excel file from the Nobel Committee webpage, and not the Excel file, but the text is from the Nobel Prize Committee webpage. And so looking at that, one might find that there is a dark matter or dark energy prize. I don't know. I'd have to look again.
So we got here Reinhard Genzel, a supermassive compact object. So apparently this Reinhard Genzel got a Nobel Prize for something about black holes. Is that right?
Maybe, yeah. I don't know. In real time, perhaps I could open the Excel file
All
and
right.
look at.
I'm just asking. I'm just asking about that. Okay. All right. So we do have some cosmology prizes here in your figure 3, but not in your first figure.
Uh, I think less so in the first one.
Didn't see any in the first one. Okay. Well, we're coming up here. We got like 8 minutes before we.
There's one black hole formation, Penrose.
Oh, right.
In
Okay.
table 1, which I think is superseded by the binary mechanics cosmology. Now, if we go down here and look at table 3, the ones which are more in agreement with binary mechanics work, we find the supermassive compact objects was by Genzel et al. Was listed in this table in relation to binary mechanics cosmology paper, because that binary mechanics paper does recognize the formation of supermassive objects by the law of motion.
Okay.
So they're basically in agreement.
I
What's
guess they
binary
didn't.
mechanics position on black holes?
That they're more or less fiction because you can't have an infinite density.
Okay. Well, they're trying to worm their way out of it, as I talked about that last week, where they're invoking quantum laws to sort of avoid the singularity in black holes and at the origin of the universe.
Well, to the extent that they would even try to do that, indicates a severe limitation in the quantum laws that they're using.
You can conceive of a super dense area of space, which is not a black hole. The black hole description is normally given to the singularity, which you're not using. You're objecting to.
Well, I'm looking at the Nobel Prize for Reinhard, and they didn't get the memo. The scientists didn't get the memo. Cosmologists didn't get the memo. They still describe it. A black hole is a supermassive compact object with gravitational forces so large, nothing, not even light, can escape it. Well, we see jets coming out of these areas, and
Well,
they're
the jets
spitting
are
out.
formed outside of the black hole. That's the trick they play.
Well, yeah, okay. Well, I doubt that's the case. I think
Yeah, I
it's
know. I just think black holes are controversial, and I don't understand how they can claim that they really actually prove they exist, and nobody even questions it. It just strikes me as you
yeah,
know.
I get that, and I understand that, and I agree with it too, because we think in the electric universe that they're a plasmoid at the center of of each galaxies, and sometimes you can find them in arms of galaxies. It's just a plasmoid with electrons being shoved into it from the Birkeland currents that they sit on.
Okay, let's see. We got 4 minutes here. Anybody else with any comments? Wow, we're done already. Well, what are we going to talk about in the next 2 sessions?
Binary mechanics.
Well, I could send another paper. I have
Excuse
two
me?
more recent papers, not on Nobel Prizes. One's on proton radius, and another one's on the fact that the Pauli spin matrices actually define a cubic structure, which leads to binary mechanics. So that the quantum mechanics people have actually been uh, favoring the binary mechanics approach of a cubic lattice in space, but just didn't know it because they didn't understand the Pauli matrices. So that's another paper that I could present with the click of a mouse.
Well, this is interesting because I find that, this is Ido, by the way, I find that my thoughts often resonate with Jim here, very often, and I dare say we even think alike a little bit. But this is a thing where I'm definitely going to fight Jim because he uses the cubical and I use the spherical approach, of course. So I would argue, Jim, that applying this also leads to the structured atom model, but then with spheres instead of cubes. So it's cube versus spheres now.
All right. There should be a diversity of approaches.
Exactly.
I have no problem with that. Unfortunately, some of the people here, I won't mention any names, but they want to exclude other approaches.
Right.
And I don't think that's appropriate.
Well,
What if everyone agreed on everything? What a boring world this would be. How astrophysics would be so boring if everyone just agreed on everything.
well, see, that's where I agree with you immediately again. So this will be an interesting thing. Yeah.
Well, I'd be delighted. Some of the Nobel Prizes, by the way, were awarded for what is essentially a measurement artifact, like the radius of the proton. My proton radius paper points out that, which we can take up in the next session if Harry so desires, is actually alleging that the conventional proton radius is a measurement artifact. And some of these Nobel Prizes were given for artifacts and not for correct measurements, which is really, normally an experimental artifact or a measurement artifact, I should say more precisely, is something that brings sort of shame and disrepute to the investigators involved, not glory and Nobel Prizes.
Well, the proton radius, I'm just supporting the idea to present that very much so because it is a key point, I think, in cosmology and nuclear physics, both of them.
Well, in that paper, I'm calling into question a lot of nuclear physics, and
Right?
I'd be glad to click on that for the next session. It's a short paper, okay? And I seem to have gotten over my cough. I really apologize for that. I just woke up from a nap before this session, and I guess I was really congested. So I apologize for all those coughing interruptions in my talk. I think I'm sort of mostly over that now. I've cleared my throat.
Okay,
Cleared
we're
the
coming up to the end. All right, anything else? You got maybe 20 or
Well,
30
even more
seconds?
Well,
generally, I don't know if you want to address more extraneous points about whether Nobel Prizes have been awarded on rational scientific bases alone. Perhaps political considerations and considerations of PR, what the media would be interested in and what people's imaginations would be captured by. In other words, how logical and rational is the awarding of Nobel Prizes, or has it been since 1900?
Why don't we
Yes.
take that up after Jim gives his okay. Yeah, I was gonna broach the topic that you brought up, Ian. And I think we should discuss that certainly before we end this particular meeting. So Jim, why don't you go ahead and give your little short presentation that you have, and
Okay.
I got the recording going. It looks like, okay, so we're recording. Okay, go ahead.
Well, I just wanted to reply to Ian's what I think is a valid point, and it could be these steps in um, uh, the lifetimes um, agree with Ian's analysis, and that maybe the political circumstances or composition of the committee or other factors are explaining why these steps appear. It doesn't seem to be random in these lifetimes. Oh, okay, let's see if I can go to, we want the radius one. Okay, let's see if that one comes up. Am I sharing this now or?
No.
No,
No.
you didn't send me a share request.
Oh, okay. Send request. And now to share. Here we go. Share. So let's see. Abstract and introduction. This would be a case of a measurement artifact. And it would be interesting if the work of these people, which supposedly resolve the issue of the proton radius, will receive a Nobel Prize. And here I'm claiming it's an artifact.
Okay, I'm not sure I understand that. Could you give us some background about what you mean there?
Yes, let's see, a measurement artifact is a conclusion or a measurement which leads to a conclusion which is actually false.
Well, has this work been done recently? Is that what you're referring to, or what?
Well, that could be done at any time. I was just trying to respond to what you said in terms of a definition of what a measurement artifact is. And it could
It's
be.
not what I meant really. You seem to be saying that there's been some recent work on this that the Nobel Prize may or may not be awarded. I got
Yes,
confused.
there was a puzzle about the 0.84 femtometer proton radius measurement that there was some discrepancy. Was it 0.89 or 0.85 or 83 or whatever? And now, if you Google proton radius, you'll see that they're proclaiming that this has been resolved. And in fact, this puzzle is now solved, and the actual radius is 0.84 femtometers. Does that address what you were saying, Harry?
Okay, so this is a recent claim that it's 0.84?
Yeah, according to Google.
It's a bit of an
Okay.
ongoing thing. We have been trying to discern what the actual value is more and more and better and better. And as Jim pointed out, there's more or less a consensus right now about at the 0.84, more or less.
Okay, so here's the headline where I go up against this.
Okay, so let me ask the question: is there going to be a Nobel Prize as a result of this, or is this?
Well,
you know?
that's a very, very good question. If there is, it'll be another Nobel Prize with a negative lifetime, because see, the publication of this paper we're looking at right now, my paper, is 2026. So if they go ahead and give a Nobel Prize in subsequent years for this proton radius thing, it will be have a negative lifetime. In other words, it will have already expired.
Okay, so your argument here is that you're claiming that your theory produces a result of 1.34 femtometers compared to their claim of 0.84.
Correct, and this paper explains that.
Okay.
So we have proton size is presently estimated by measurements of proton charge radius. Charge radius, okay, of approximately 0.84 femtometers. In contrast, based on binary mechanics postulates and equations, reported proton radius is about 1.34 femtometers, substantially greater. This substantial size discrepancy may be resolved by data indicating that the proton charge radius may underestimate proton size because 3 parts of proton structure contain concentrations of positive fractional charges, as shown in figure 1 here. The black arrows point to a group of 3 positive charges on the periphery of the proton structure in the proton cycle in 3 different locations. So, okay, and so let's move on down and explain this a little bit. Methods and results, proton-hadron structures and cycle. Discovery of the proton-hadron cycle in 2011 revealed a 42-component structure in which energy quanta rotate in a clockwise direction in the perspective shown in figure 1. Each component is a quantized location of 0 state, empty, or 1 state energy quanta. Thus, the proton cycle has 2 to the 42 possible configurations, accounting for a wide range of particles and particle states and energies. In figure 1, 2 types of location are associated with energy quanta have been defined, M and L. M-type locations exhibit a fractional 1/3 charge attribute, plus or minus, when in the 1 state. The L-type locations exhibit a directional property, and these are the orange arrows in the figure above. You see the orange arrows there pointing in different directions. 6 different directions to be exact.
They look like yellow, actually.
Okay, we could call them.
We'll go
okay.
back. Am I wrong? Or they look like yellow to me?
Okay.
I think he's talking about the spheres.
Yes, the
The
pointer.
orange arrows here
Oh,
are
okay.
the L-type locations in the proton structure. These what I'm calling black arrows, which do have a yellow center, yes, Harry, you're right, are the ones at the periphery, which form 3 1/3 fractional charges, which adds up to 1 elementary charge. And these could be like parts of the elephant, as it were, that people are observing in actually publishing a measurement artifact. So let's continue.
Forgive me the interruption, sir, but I do have a question that may be important. Why are you using the 3 charges? I'm not sure I picked up where that came from. Why is it there? 3 charges instead of just 1 charge, if you will.
Well, there are 3 groups of charges.
Why? Why is
there?
There
3 groups of 3? Well, that's the discovery in 2011 of the proton cycle. Okay.
Okay, that's what you base that on. Okay, right.
Yeah, exactly. Yeah. Yes, sir. Thank you for the clarification. In figure 1, we've got the 2 types of location. The L-type locations exhibit a directional property, the orange arrows, indicating 1 state motion direction due to electrostatic or magnetic potentials. The proton cycle exhibits a structure with 3 groups of black arrows of positive fractional charges located at 90-degree angles to each other, upward, lower left, and lower right. Upward, lower left, and lower right. 3 groups. And so if your charge radius type measurements based upon charge radius is seeing only one of these groups, you're going to underestimate proton radius. That's sort of the punchline in all of this. Okay, non-spherical proton shape. This was reported in the scattering experiments back in the last century. Integer coordinates may be assigned to the quantized locations shown in figure 1. Now we're jumping to my results. The proton cycle locations are asymmetrically distributed in this space, as shown in figure 2, where we have two X-ray views illustrating a non-spherical proton shape. Considering a third XZ view, proton structure features a non-spherical shape, and it's quite clear. There's no doubt about it. Let's see. What did I do? Okay. Work by G.A. Miller has suggested that observed non-spherical proton shape may be a deformation of a spherical ground state shape. In contrast to Miller and conventional quantum chromodynamics refers to work related to proton structure. Analysis by the author cited above suggests that a non-spherical shape is a fundamental property of proton structure, even at the lowest energy levels. In other words, it's very different from what the Miller group has suggested. Proton size, according to the coordinate system in figure 2, for the centers of each location, the average location position or center of gravity is 2, 2, 2 in quantized length units in the Keene scale. Location radius is its distance from the center of this center of gravity, and the average radius is, again, 2 length units. Each length unit in this Keene scale is about 0.67 or 2/3 of a femtometer. The average location radius, therefore, in figure 1 is approximately 1 1/3 femtometers. Proton location radii varied from 0.95 femtometers for the inner loci to 1.65 and over 2 femtometers for each group of the 3 outer loci arranged at 90-degree angles to each other. Figure 1, the black arrows that we've talked about. Proton electric dipole moment. For review, everyone knows that the water molecule has an electric dipole moment because the 2 hydrogen atoms are not symmetrical around the oxygen atom in a water molecule, and that the positive charge of the related to the hydrogen results in what we call an electric dipole moment, or a lack of symmetry in that, or an electric dipole occurring in the water molecule. So the proton also itself has an electric dipole moment. As reported by Binary Mechanics Lab, the structure contains 21 positive and negative fractional charges. The net fractional charge is +3, consistent with the observed proton overall elementary charge of +1. Figure 3 shows 2 views of the distribution of fractional charges in the proton structure volume. Let me scroll down here a little bit. This density and charge sign distribution establishes a non-zero proton electric dipole moment. In agreement with Olive et al., considering a third XZ view, which is not shown here, we have the YX and YZ views. The data exhibit 3 regions within proton structure at 90-degree angles to each other, where proton fractional charges are concentrated. Binary Mechanics Lab calculated proton EDM equals 8.5 to the minus 32 ECM with 1 quanta in the proton cycle, and up to 8.5 to the minus 31 ECM with 10 quanta in the cycle. These BML results are consistent with the upper limits for proton EDM estimated using mercury 199 atoms placing the constraint at less than the values given here that I'm pointing to. I won't even attempt to read them all. Discussion, another proton radius puzzle. That's where we started this little talk. The 1 1/3 femtometer proton radius based upon the proton cycle is substantially greater than the reported 0.84 femtometer proton radius based on proton charge radius measurements. These measurements estimate, and their 0.84 femtometer estimate may be an artifact of the measurement method based on charge interaction events. In other words, the 0.84 femtometer result for proton size may be consistent with measurements of one of the three fractional charge groups at the proton structure periphery shown in figure 1 with the black arrows. In sum, the three groups of three black arrows each. In sum, this 0.84 femtometer result may represent parts of the complete proton structure. In short, in support of this interpretation, the approximate 0.82 femtometer electron radius was reported in the BML derivation of Planck's constant H entirely from first principles. The 0.82 femtometer electron size is close to the size of just one of the three fractional charge groups in the overall proton structure shown in figure 1, blind man and the elephant. This report may illustrate the familiar fable about the blind men, and elephant. That story shows that researchers may tend to believe a limited experience, proton size based upon proton charge distribution, and ignore other valid perspectives, such as the proton size based on the proton cycle discovery by yours truly in 2011. Thank you for your attention. So here we have the story of the blind man, and the elephant producing a measurement artifact, which, as Harry has pointed out, could easily be awarded a Nobel Prize even after that work has been debunked, as I just presented.
Well, thank you for this, Jim. This really leads me to, since I don't know how they're doing this measurement of 0.82 femtometers, I'm assuming they're probably shooting particles at other particles and then looking at scattering results and that sort of thing. But I have no idea how they're doing it. And what you're claiming, I'm assuming that this 0.82 electron radius implies that a proton is a spherical object. That's what it sounds like to me. Sounds like they're assuming that it's a spherical object.
Oh, yes, they do. In QCD, quantum chromodynamics, it's all about a sphere, even though for years, experimental laboratories have reported, as I have cited in my papers, before my work, well before it, that their scattering data indicates that the proton has a non-spherical shape. But of course, this result being in the previous century is just simply ignored.
I would like to bring some doubt to the table there about the scattering data. Coming from a structured atom model perspective, sir, so different, yeah? If I look at the structure, and everybody I think can do this, if you take 4 spheres in mind and you put it in a tetrahedral shape, I'm sure everybody can do that. If you look at any side from that in 3D dimensional, so you have a spherical tetrahedral form made up of 4 spheres, that means every sphere that you take on its own is connected to 3 other spheres. If you're going to use scattering data, I doubt, but I can be wrong here, I doubt they used loose protons to measure. So I'm assuming they used at least
What
some
was that,
heavier...
Ido?
Sorry?
What is a noose proton? Or loose? What was that word you used, sir?
A single. I was struggling for the English terminology there.
Okay.
I do apologize, not English native.
Thank you.
If you take a single proton in isolation in that tetrahedral structure, it is connected to 3 other protons, right? Simple logic, just no fancy stuff there at all. What I'm trying to say here is this. If you're starting to shoot other electrons or protons, whatever, at them, at that tetrahedral form, it is quite easy to imagine that instead of just hitting the center, if it's just off, you're going to hit one of the other three protons behind it, if you will. That would result in a free, as you point out, these free charges. That's why I said I want to bring some doubt to the table. So coming from structured atom models perspective, whereby accepting there's a specific structure for the nucleus, as I propose in the structured atom model, you would come to a very logical conclusion as to why this scattering data shows these distinct free charges or free regions or free quarks, right? And within the structure.
Okay, the
Yeah.
your argument there is has a lot of merit if you're using helium atoms as the target.
It depends
But
on
if
what
you're
atom you
using
use, sir.
individual protons as the target, one might say that none of what you just said would apply
Correct.
to present analysis.
Correct. I don't know what they shot at. So if somebody can shed some light there on what was the target, if you will, but I highly doubt it would be single protons, hydrogen one. And on top of that, just to give the merit a little bit more merit, perhaps, again, I cannot prove any of this. It is a perspective coming from the structured atom model dealing with the free quarks or the free charges. Why one proton would have free centers, if you will, right? I think it's a residual or artifact from the actual structure. So at one point, I dropped a comment to another a friend of mine from Minsk, Belarus, who studied the quark realm very much. And so I told him, it's a shame that there are not 4 or 5 quarks as well, because my structure that I propose shows that in the larger nuclei you can also have 4 or 5 connections. So 3, 4, 5. That would be the numbers, no more, no less. And he drops back to me, well, a pentaquark and a quattro quark, I can't remember the distinct name there, but pentaquark I think it was, so 5. These things are also reported on. So I still argue that it is a artifact of the actual structure that the protons make. Again, no evidence, no proof. I'm simply putting it forth to as something to consider, perhaps.
Well, this latter point from Ido, our dear friend, has emphasized the point that I'm trying to make here, that measurement artifacts can and do occur. What I'm saying is that the blind men in our elephant example, in that fable, are looking at portions of the proton structure, one, and then lower left or lower right, and confusing that for the entire proton because they are specifically attempting to measure charge radius. And they're confusing charge radius with the total structure of the proton itself. That's my one sentence summary of this paper.
Right.
Okay, well, that leads you to the question of how are they making these measurements, which I have, now I'm asking myself, how do they make these measurements? Yeah, okay.
What they're
That,
doing, I'll tell you how right now, as far as I know, they are shooting charged particles, which are electrons or protons, at each other, and determining the radius based upon the scattering from those collisions of single.
which implies that they must have some kind of sophisticated detector arrays and computer calculations to process all these measurements.
Correct. And and they're very antiquated things as far as the technology of particle research methodology goes. These are really antiquated, like you'll find them at CERN. It's like going back a whole century. If you look at with a critical eye at what they're actually doing, they're so far behind current advances in particle physics. It's like going back in time to visit a tribe that has been isolated from the world for decades. At any rate, forget our time machine. What we're showing here is that if you're trying to use charge radius as a measurement of total proton radius, shown in the figure illustrated now, you're going to possibly, and I think definitely, confuse these groupings of charge, the three of them that I'm pointing out here, as the proton radius when there are essentially in the fable blind men looking at parts of the entire elephant and confusing those parts with the whole elephant, as it were. The whole elephant would be the proton cycle structure shown here.
Could it be, sir, that your groupings that you point out here, could it be the other way around, meaning that the groupings are a representation of the actual connections that would be there, meaning the dependency is the other way around? So instead of having these initial groupings, the structure would force a specific grouping, if you can follow my logic. So the grouping would reflect the actual structure between the protons. Is that an option in your mind?
Well, you said protons in plural. This is showing one proton.
Yes.
So I don't
But
follow.
Could it be that one of your specific groupings here of one proton, right, with the free charges there, could that be the result of the greater structure? So, for example, the alpha particle, the helium, right, the tetrahedral, then you would, because that structure is there, the individual protons would have to have a specific grouping that you're pointing out here, right, in the free charges. So it would adjust itself to the larger structure. I guess that's my question. Is that a possibility in your mind?
Well, I don't think so, but that the situation you describe, I think, does require further thought.
Right.
At present, the structure shown here is the 2011 discovery of the proton cycle. And that comes from the Binary Mechanics Lab simulator, which everyone can download, by the way, and see for yourself this structure. And that's where I'm at the present time.
Okay. More thought needed.
Yeah, I think I understand what you're saying, Ido. You're saying, are they measuring, or is this measuring other aspects of structure? And the assumption is that you're shooting at a lone proton. Isn't that the assumption that these scatterings that they measure are coming off of lone protons?
That's correct. And they've shot electrons at protons and vice versa, and get the data from that. And so when they are measuring proton radius in terms of the charge radius that these scattering results indicate, I am alleging that they are, in fact, because of the proton structure shown here, measuring only part of the total proton structure and therefore underestimating the true radius. So that in my book, the whole puzzle about what is the proton radius is still a puzzle, or there's still a major discrepancy that exists. And I put forth my view in this paper.
Do you have any ideas on how to do this in an experiment, if you will, to be more to shed more light on this? Do you have any ideas what should be done with an experiment to get this result, if you will?
Well, the experiments that have already been done, I think, do get this result. The result is that they're looking at part of the proton structure and detecting a total charge of elementary charge +1 based upon 3 fractional charges in part of the proton structure. So I'm not
You
sure
go
exactly
down to the go down to the diagram where you show that, the figure where you show that.
uh,
Yeah, you're claiming that these I thought the one that was above this, the previous one, was a little more. It looks like you're showing there that they've measured these 3 groupings. That's what your assertion is, I believe.
no, that's my measurements based
Oh,
upon
this is your predictions?
X-ray views of the proton non-spherical
Okay,
shape.
that's not what the measurements were. The one below it is the measurements. Okay. Now
No,
I guess
the one below is also from my lab.
okay, but I thought these represented measurements. Okay, I'm sorry for misunderstanding.
No problem, sir. The measurements are the point 0.084 femtometer radius that is being detected, and
Right. But
all
you
I
were saying the implication I got was that you were saying that the group, uh, what was the name of the group, Miller or somebody?
yeah
Um, they had detected some structure other than a spherical structure. That
well
was that
Miller
non-observed, non-spherical proton shape.
yeah
So
and
they
yes, they have claimed that the observed non-spherical proton shape, so they do acknowledge that there is data supporting the idea of a non-spherical proton shape in agreement with binary mechanics analysis. So there's
okay.
agreement there, but their explanation is quite different. That it's a deformation of a spherical ground state shape, whereas in binary mechanics, I'm alleging that the non-spherical shape is a fundamental property of proton structure, even at the lowest energy levels. It's not due to some deformation at a higher energy state, which could definitely occur because
So what you're saying is the Miller group is sort of explaining away the discrepancy rather than accepting it as a valid result.
that would appear to be a fair statement of the Miller position, I think.
Okay. All right. I think I understand this better now. All right. Thank you.
Well, and thank you for helping to clarify it, sir.
All
Now,
right.
if we want to go for a trifecta, I haven't looked at the time. Okay, there's 7 minutes more here, or 6 minutes. If we want to go for a trifecta, I have another short recent paper which indicates that conventional quantum mechanics has mistaken the meaning of the Pauli spin matrices, which in fact define a cubic structure or a cubic lattice in space in agreement with binary mechanics postulates. So if we want to go
Okay,
to
that sounds a little
I
that
I'd
sounds a
like
little
I'd like to propose a question.
yes, please.
Could the act of measuring the proton itself be deforming the proton?
Well, it could be definitely
I think that's what Miller is claiming.
well, if the interaction of two charged particles occurs, then one might definitely expect that the states of the loci in the proton structure could well change from 0 to 1. Like, for example, if these 3 plus loci are in the zero state, there would be no charge there, no net charge. So, but if all three are in the one state, and definitely as particles interact, these states, all of these states are subject to change. That's just because we're talking about a universe which is up and running. It's not static.
Right, but if the force is coming from one side of this structure, would it not deform it slightly?
Well,
And or if it's a sphere, would not that force deform that sphere as
well,
it's encountering it?
the simple one-word answer is no, because the whole axioms of binary mechanics are that a cubic lattice structure is intrinsic to space. That space contains a cubic lattice structure, which would be in the third paper for today if we want to venture into that. And by the way, that's much shorter even than this one. This one was the longest paper, and it's was done in less than one session.
But I think in the real world, you could use, the analogy of somebody kicking a ball. See that at slow motion, you can see a deformation happening on the ball as that force is applied to it.
That observed deformations of that nature would be changing of states between 1 and 0 in various loci in the proton structure, which, by the way, forms a proton network. And so that all of those apparent deformations in the shape are actually changes in the state of the loci within the structure. Two ways to look at it.
Yeah.
And the basic thing, Rick, in your good question is that you're assuming continuous space and time in the basic axioms, in the foundation of every thought that you have about physics. In binary mechanics, we don't assume that. We have quantized items in space, time, and energy. And we don't assume that continuous nature that you're assuming. And so it's sort of like puberty. Once you quantize these three items, space, time, and energy, it's like puberty. There's no going back.
If the proton, I believe when we fuse things together, so we form a deuteron or form a helium, lots of energy is emitted. E is mc square, meaning some mass is emitted in the form of energy or light, we say. That means in my book, and I'm not sure if you, I think we talked about it, Jim, but I'm not sure now. In my book, that mass or energy is sourced by the protons, meaning it would imply that the protons change their mass, a little bit less MeV or atomic unit, mass units. Do you think that could be reflected in your modeling here, or is that something that you don't even think is viable?
Well, in the binary universe of binary mechanics, mass is not a constant. Okay.
I agree there.
In other words, the fact that we think that the proton mass is about 1,836 times greater than the electron rest mass is due to our assumptions, because the mass, if all 42 of these.
Okay, Jim, you got interrupted there. I should have warned you.
Well, let's put it this way. For the electron spot, it has 6 locations. Now, we got 42 locations here in the let's, I guess I need to share my screen, right? Let's see, here we go. Share request. Share, send request. Share, choose a application window. Okay. I'm trying to get back to the paper here.
Well, you had it
There.
there a second ago. All right, there it's
Yeah,
okay.
I made the mistake of clicking on the fake figure, which brings up just the fake figure itself in the browser. At any rate, you notice that there are 42 locations here in this cycle, and there's 6 locations in the electron cycle. Divide the two numbers. 6 into 42 is what? 7. So the proton mass should be 7 times the electron mass at ground state. And so the mass that we're using of the proton mass being, or almost 2,000 times greater than the proton mass shows one thing, that this depends upon energy density in the environment. So in other words, particle mass as measured in today's laboratories is not indicative of actual ground state mass. And or another way to say the same thing is the mass is not a constant. And so the depiction in physics literature of the proton electron mass ratio is another measurement artifact in the sense that is implying that that's a constant when it's not at all a constant. In fact, that ratio actually increases at even greater energy densities. So if you're using these numbers in your calculation, you really have, well, you might say little chance in hell of coming up with any kind of a reasonable result.
Well, that's the problem, isn't it? Because it's charged particles in a field, and then the amount of resistance, and then you can do your computations, and you can, calculate the mass. And the energy density, if this is true, what you're saying with the energy density, and that's something that crossed my mind too, that would give you different values. So, wrong measurements between brackets, if you will. But the assertion that the proton is 1/7 of the electron is 1/7 of the proton in mass-wise, I would like to see a little bit more substantiated evidence there. I think that's difficult to reconcile with the existing data sets, is what I'm saying.
You've got a good point there.
Okay, we've had, I'm not sure, I think we want to introduce another subject topic here at the present time. And so perhaps you could give the other presentation next week or sometime in the future because we don't have anything scheduled for next week.
That's fine, Harry. I appreciate the hospitality you and the group has shown. Thank
Well,
you.
we need to, I'm basically suggesting that if we use up all the available topics right away, we won't have any in the future. So we need future topics to talk about if we want to keep going here on Sunday mornings.
Okay, can I bring up something completely new then, if that is appropriate right now?
Well, fine. I do want to get to Ian's suggestion that we discuss what a Nobel Prize is about, which I think that's
Please stick to the plan, sir.
um, but you can
Make
go
it
ahead. Ian, do you want to discuss this issue about Nobel Prizes?
Yeah, I'm just wondering, what is basically Ido's new point? I mean, is it something we can deal with next week, maybe, at the other
or
presentation?
or make a show out of it.
Yeah, I mean, what is it roughly? Is it about what Jim has been speaking about today, or is it about what I'm suggesting now, political things? Just roughly, just in one or two words, Ido. You said it's a new thing.
Oh, I'm sorry. The thing is this. In the 1933 Solvay conference, and I'm going to quote here, if we can say that a neutron is composed of a proton and a negative electron, so we can say that the proton consists of a neutron and a positive electron, positron, both reactions, so meaning free neutron decay one way and the other way around, creating a free neutron, if you will, are necessarily both possible or both impossible. End quote. This was done by Mr. Perrin during a debate about the nature of the neutron. From that postulation comes the acceptance of the free neutron being a fundamental particle, which leads to cosmological acceptance of things like a neutron star. And the whole debate there, I would like to, at some point, but perhaps this should be a mini presentation too, that's why I bring it up, because if you follow the logic is this: a nucleus consists of protons and neutrons, but the relationship is not understood, and the neutrons are stable within the nucleus. The neutrons individually, free neutrons, are not stable. So the whole problem here is this: it is a misconception to say that the neutron is a fundamental particle, because the neutron can only be stable when it's combined with protons. And that is the fundamental postulation that I have with the structured atom model. And the acceptance otherwise, and this is what I would throw out in the audience here, perhaps in the next session, that we need to look at this, because it leads, the ratio within the nucleus should be 2 protons, 1 electron, or, as quantum mechanics states, 1 proton, 1 neutron, and then the neutron is stable. If you forget and omit that relationship, and you just look at the free neutron decay or the other way around, then you can come to this wrong conclusion. And I would like to, I don't know, point this out, emphasize it, show the whole world how critical of a postulation and conclusion this is, and that led to things like a neutron star. And, well, that's an impossibility in my mind already. There you go. So that's a topic that I would like to bring to the table if there's enough support there. Otherwise, forget it. But you know,
Ido, what if neutrons are not stable even if in a nucleus? In other words, which proton contains an electron and therefore is called a neutron, can change over time, and so that in a nucleus like helium or lithium or higher Z atoms, which one is the neutron and which one is the proton is not a fixed thing.
That's the point.
The whole concept of you're stating that there are stable neutrons is called into question, is it not?
Well, that's the quote I just read from 1933 was the debate about the nature of the neutron. Is it a fundamental particle? Is it a composite between protons and electrons, right? That's the debate here that I'm referring to. Now, the arguments were made, and what I'm saying is the protons within the nucleus are simply protons. So you have 2 protons sharing 1 electron. That is the basic system. That is the postulation I have, my opinion, my bias, if you will. But that's what I hold, because that is the ratio that holds true with the stability of every element that we know, right? So it totally jives, meaning the ratio is not 1 proton to 1 electron and then arbitrarily say that proton belongs to what we call the neutron. There is no neutron within the nucleus. It's 2 protons kept together by Coulomb forces, I postulate, by the electrons sitting in between, which
in the deuteron.
That's the deuteron. And that system, the deuteron, now who do you want to point out as being the neutron? There is no neutron because it's not a fundamental particle. The neutron, in my book, is a misconception as a fundamental particle, and that is because they ignore the ratio in the nucleus, if you will. So if you only take the free neutron in mind and you base all your conclusions on the free neutron decay, and then you postulate it has to be the other way around too, only you use the positrons here, then you come up with these fallacies, I would argue, like a neutron star. So, these things in fundamental physics, nuclear physics, lead directly to the acceptance of neutron stars in cosmology. I'm just pointing that out. But this is the 1933 historical debate, and that's what I would like to point out in the future session, just to show it everybody, perhaps go through it a little bit so we can understand where this came from and the logic. And if we take the ratio into account, 2 protons to 1 electron, which one is the neutron? You take your pick. I say none or all.
Yeah, save it for another show.
Okay.
Okay,
Well,
I think
that's what I wanted to.
that's
Yeah.
a good suggestion. Why don't you give us a talk about that?
Yeah, I was afraid for homework already, so I should have shut up, but I will do it. I think it's
Um,
I think it's a really important topic, and it
but
shows a
you,
direct link from the nuclear physics to the cosmological concepts. So that's pretty
okay,
neat.
That would be a good idea.
a
Okay.
comment that I have to make about that, which I think you brought up kind of indirectly in your suggest, and that is when people get Nobel prizes for things, okay, they become fixed in concrete. Okay, and I think that's the issue here that you're saying is that this idea that the neutron is a fundamental particle, and you think that that's not really that it's not really a fundamental particle. That's a
Right.
wrong idea. But that idea, people get Nobel prizes. I guess Chadwick got a Nobel Prize
Yep.
for the discovery of the neutron, and that means that it's now inviolable. We can't contradict what a person won a Nobel Prize for now, because so that becomes
Correct.
cast in concrete. And I think that's, and then the question is, how does this process of determining, to me, if you give somebody a Nobel Prize for a discovery in physics, that's a lot of responsibility there, because you're declaring as a Nobel Prize committee that this is a discovery that can't be contradicted ever again in the future.
Well said.
And I
have
think
you ever
this neutron case, what you just pointed out, yes, sir, I totally agree. And this specific case of accepting a neutron as a fundamental particle, the more I dig into it, it lies at the very, very heart of lots of problems with cosmological, quantum mechanics in general, quantum everything.
Ido, when you present this, I hope you take up the whole question of neutrons being ejected, and why it appears that it is a particle with a particular lifetime, and which decays rapidly,
Right.
and so what it appears that you're saying is that for some reason the proton and the electron are ejected exactly on the same trajectory to be mistaken for a neutron being ejected as a entity. So I hope you take up that when you present, because
Right.
that would appear to be a contradiction to this whole idea.
I can point out the things. I do not have an answer for you, but I think we would be in agreement to point out that is one of the most crucial fundamental research topics that we could have right now. It would shed so much light on so many topics.
I agree.
Why this is? Why is it with a specific value emitted from the nucleus? The nucleus basically splits, but the smallest split possible is, emit a proton. But a proton emission is basically naturally impossible. Only when we really, really mess things up with high particle accelerators we can do that. Otherwise, nature only uses beta the beta decay the other way around, meaning beta minus decay, that's the natural phenomenon. And then we have the things like an alpha particle emission, we have a free neutron emission, and we need to understand why that is and why that happens. And I can shed some light on it, but I don't have all the answers. I think this is an absolutely crucial research topic. All I'm trying to say is, and that is, I'm in the camp of a composite particle, obviously, right? If you treat it as a composite particle, a temporary combination still between an electron and a proton, I don't see the issue here, really. Yes, there's a lot of problems within quantum mechanics need fixing according to such a concept, but
So
there's no
basically,
real.
so basically, you're saying that the neutron can be considered a particle. You just called it a composite particle.
I acknowledge, and it's the terminology that's the problem here right now. I simply don't have the terminology because what is what we call a free neutron? I acknowledge that there is something that we call a free neutron that appears to be quite neutral, right? And when it decays into a proton and an electron. And it does come from the nucleus. But it's simply, that's the only addition I would like to make is, it is a composite of a proton and an electron in a temporary state because the ratio is broken. There's no longer two protons holding that one electron in the nucleus, in the nuclear state. Therefore, it decays. That's what we need to study and wise up on, how that works, why the specific energy levels of 0.782 MeV, for example. We don't have the answer there.
Let me interrupt here, but it doesn't, when this decay occurs, you also get a neutrino.
Allegedly, but that's to fix the mass error.
Right. So their claim is that there is a neutrino created, and that's another
Yeah.
controversy.
Yes, I don't intend to run away from what you said there, but coming from the structured atom model point of view, meaning that the neutrons should be a composite particle, there is no need for a neutrino or an antineutrino at all. There is no need for it.
Okay. Okay. Well, this is a broad topic.
It is. It touches
And
everything immediately the moment you touch the neutron. And I guess that's part of the answer to the question or the things that you pointed out, Harry, with the Nobel Prize winning. The moment you touch it, it's like when you live in a monarchy, which I do. Once laws have been went through the crown, it's definitive. It's, you can't go back. No, there is no more going back, if you will. And it feels like this is the state of physics as well. Chadwick got his prize for the discovery of the neutron with that and that mass, and that's it, done deal. No more going back. That's how it feels.
So there are two sides to this Nobel Prize business. One is how the prizes are awarded in the first instance. How is it decided to award prizes in this particular area or to these particular researchers or whatever? And then the second side is the orthodoxy. Once a Nobel Prize has been awarded, well, then the work is considered uncontestable science, if you like. So again, it's a bit like we've said in the past.
Yes.
Sort of councils of the church, or for example, you decide what the councils decide who should be respected interpreters, whether Saint Aquinas should be considered, an orthodox interpreter, or maybe other people are heretical and they shouldn't be considered, or maybe some rabbi interpreting some bits of the Talmud or something is accepted as orthodox, but another one is considered not so orthodox. So those are the two sides, and how are they formulated? Well, I would maintain that there are a lot of political considerations. And another thing, but by the way, I just listening recently, there was something that where they said that some of these vaccinations. I know I'm going off a tangent now, but if you permit me, some of these vaccinations. I don't know if it's the shingles vaccination, but it was found. There's some research done recently which says some of these vaccinations have an added effect, which are unrelated to their primary effect, in that they can ward off dementia. So some of these medical people are saying that's marvelous. That's another reason to get the shingles vaccination. You'll have less chance of getting a dementia. Well, this research, I haven't looked at the research myself, but it's being welcomed by the medical establishment. Now, suppose there was a piece of research that came out that some of these vaccinations would actually be productive in bringing on dementia. Well, I'm sure the medical professions would come together and they would say, this is crack science and we'll have to destroy it and so on and so forth. So there's a preconceived idea. Another example one might give is why were no Nobel prizes awarded for dissident physics? There's a good question. They're all
Well, dissident physics is by definition wrong.
this is the point I'm making.
Ну,
Yeah,
Нусенька.
you've decided
Вообще
before.
весь этот шум туда распространяется, куда я разговариваю.
Okay, Vladimir, your mic.
Давно уже надо сообразить.
Okay,
Никакой же
go on,
срочности
Ian.
нет в том, что ты
Yeah,
делаешь.
Vladimir.
Vladimir was speaking there.
No, I'm sorry.
It's all right.
I'm talking to my wife. It's
Okay.
very interesting for me. I know nothing about all this elementary particles, all quantum physics. That's why for me, it's a new knowledge, Especially I do like the idea two protons and electrons combination, I do like it as a physicist.
Okay, go on, Ian. Thank you for that, Vladimir.
Yeah, okay. I'm amenable to it as well, by the way. I haven't said much. But yes. So I think it would be very interesting to do a sociological study. It hasn't been done. We're just making comments, we're making observations. But if somebody proposed doing a doctorate in analysis of the Nobel Prizes, maybe not restricted to physics even.
I'm sure this has been done, actually. This is the sort of thing that some of the philosophy of science and history of science people do.
Yes, and Bob may have something to add to that. But I fear, and I hope I'm not too biased now, I fear that a lot of this would again be from the orthodox point of view. And possibly if one came in and had some initial ideas, maybe similar to the ones I just expressed, one wouldn't be permitted to undertake this research in an established academic institution. So I'm a little skeptical about all this. It's very political.
Ask for one question to Jim. Jim, let me ask you the question. My father, physical father, was Alexander Prokhorov. He has got his Nobel Prize in 1964 for masers, lasers, and all this quantum equipment. Right now, we cannot live without. How it fits with your theory? Because I'm a laser physicist, and I would like to know what you explain from my life.
Well, that would be in my table 3 as something which is still relevant today.
Because right now you did put Prokhorov not in table 1, not in table 3. There is no respect to my father. I'm sorry.
Well, as I pointed out, both tables 1 and 3 can be updated because most of the Nobel Prizes are in my database in neither of the two tables. And so I think what you're pointing out, Vlad, is that, yes, there are some which should be added. And so that my presentation today, based upon the paper I published recently on the Nobel Prize phenomena, needs to be updated and can be considered a pilot study, if you will.
I think you said 80%.
Us.
I think you said 80% weren't included in either of the tables.
That's correct. And so there's more analysis to be done, and I think Vlad has pointed out a valid example that should be included in table 3 as something which is still valid and important. I might point out in table 1, in terms of what Ido was just talking about in the neutron, that the weak interaction Nobel Prizes have all been debunked by my paper on the weak called weak interaction boondoggle. Okay, so that the weak interaction, what Ito was just talking about there with the neutron, all of those have been debunked and therefore appear in table 1.
By weak
Understood.
interaction, you mean decay of the proton of the neutron? That would be a weak interaction.
Yeah, all this stuff that the weak interaction is a primary force. In fact, I've debunked that.
Okay. All right. So we're moving forward. We've debunked the weak force. I never really understood what the hell the weak force was. I have to be honest. I
Well,
mean,
in
I've read all
binary,
these books on it, and I could never really figure out what the weak force was.
There
It's
well,
seems to
just,
be,
in binary mechanics, there are 4 equations related to system development, and one of them is the unconditional uh, uh, motion, which is actually accounts for all of the weak force phenomena. So it's really a case of a theory of weak interactions, which has been completely debunked if one has any credibility in the results of binary mechanics and its simulation experiments.
Well, again, terms like weak force and strong force are ones which are liable to be taken on by the public at large and understood. They're very good for PR reasons, for media reasons. Just as the main cosmological ones of Big Bang and you know, expanding universe, and these sort of terms, which may have been pejorative in the first place, they're adopted because they lend themselves towards publicity. It's certainly not very scientific to talk about something weak and versus something strong.
well, right, but it also, this is something that for me personally long ago was very important. In the end, it doesn't explain anything. If you're looking at beta decays, weak force interaction, right? Or what keeps a nucleus together, the strong force component that we accept nowadays, well, we, meaning in general, the only thing you're emitting is, well, there's this magical component and we're going to call it some fundamental force and that'll be that. But I don't understand the thing at all. I don't understand how, I don't understand why, I don't understand when. And that is what's been the drive for me to study this realm. And in the end, I came up with the structured data model that came out of it. But it is because these concepts are put forth as, well, we measured it, it's there, it's a fundamental thing. And if you dive into it, I can't even find, the logic often even for these concepts like strong force or weak force, or a neutron being a fundamental particle. It's all up in the air as far as I'm concerned.
and yet they gave Nobel Prizes for these
Yes,
things.
absolutely. Well, that's a question for me in general here, I guess. Where does it leave us if even the Nobel Prizes are not that noble, you know?
Well, I see it akin to magnetism and gravity until somebody quantifies it by experimentation and can explain the weak force
My God.
through experimentation, then only then will it be named. Its name will be changed from the weak force to, such and such person's force.
Well, by the rules of the prize, there has to be an experiment that confirms it. So they claim that
Yes.
there is an experiment that confirms it.
Let me ask you the question, guys. You mentioned many times force, force. Force is a classical notion. What does it mean for quantum physics, force? Can you
Good
explain me?
point. Good
Weak
point.
force.
Thank
I
you.
don't understand even this combination. Weak force.
Exactly.
Not weak, not
Exactly.
force. Let me
Exactly.
ask you the question, guys. And I absolutely agree with Harry. Forget about ideas. There is no theoretical Nobel Prizes, only experimental, only with a very good continuing of them. Suppose the lasers, they open the lasers, and right now we cannot live without lasers at all in any places. That's why this is a real Nobel Prize laureate in physics, my father. That's why please have a respect to him next time. Let me ask you a question, guys. We are talking about classical physics or quantum physics. This weak, strong force, it's not force. I don't understand it. Force is a classical notion. How you can use it? Size, you told me not femtometers and all this stuff size. I don't understand size in this level. I don't understand what is the value of it. Where is the unit of your measurement to measure these femtometers? Guys, we are talking about classical physics, then I do understand. When we started to talk about quantum physics, all these notions must be revised. Tell me the right quantum physical notions.
I don't think there's an answer to that. I
Yes,
think
this is
that's
my point. That's why we argue this one and so on and so on. Let me ask you the question. My question to this quantum physics right now and nucleus, this or that, we have some gamma radiation. It's a result of interaction of some interaction between nucleus, between something, annihilation and all this stuff. How it happens? What is the mechanism of this gamma radiation? What is the difference between gamma radiation and electromagnetic radiation? Do we have this difference? Jim, Ed, Ido, please, next time maybe answer me the question, what does it mean gamma radiation? What is the difference between gamma radiation and electromagnetic radiation? You know, there are some more specific and more important, questions to all your models. You're talking about it's a square, it's a cubicle, or this or that, physically. For me, the most important is the result. There is gamma radiation. Tell me how it goes. I don't know.
Well,
I think,
gamma is all photonic.
well,
It EM, it's gamma is part of the
no,
EM
well, hang
spectrum.
on.
And well, just let me define
Yeah,
it.
go.
They're wrong. Forget it.
EM
Forget it.
spectrum includes gamma
It is
radiation,
not
and gamma
electromagnetic
radiation,
radiation. Forget it. It's a
and
bullshit.
it's higher energy. It's at a higher energy
Higher
state than even
energy
X-rays.
doesn't mean electromagnetic radiation. You don't know electromagnetic theory at all. Sorry.
So
Okay. So now
I like Vladimir's questions, believe it or not, because many of those questions you just threw out there, I have the same questions, believe it or not. The structured atom model is a result of a long quest, of a long time of researching this stuff. And the questions that you postulate here, Vladimir, are some of the questions I have myself. And this is like an effort to answer those questions. That's why I'm so adamant about changing certain things in physics, and I guess why I find myself here talking to you guys. Because, yeah, I believe this is very important in the end. The quantum mechanics somehow prevents us, humanity in general, to reach the next level. It's so flawed, it's not even funny. But again, Vladimir, I like your questions, and maybe if we get a chance, we can talk a little bit more about some thoughts I have on that topic, but I don't have many answers because I have most of the same questions. That's my real response there.
Thought about this one because I suppose that next time it will be your presentation about your ideas, and please take into account and let's talk all of us, because what today told, it's wrong, guys. It's absolutely wrong. There are two different type of radiations: electromagnetic radiation and gamma radiation. What's the difference between them? Still I don't know how it goes, how it works. Everybody talking about it, but what is the mechanism? How it
Well,
from quantum physics, because from electromagnetic waves, I do understand from classical physics, but gamma radiation, it's not quantum classical physics. It's a quantum physics property and phenomenon.
You may be addressing the distinction between ionized radiation and non-ionized radiation. They can be both electromagnetic.
Ionized radiation, it's a gamma radiation or what? No, I have only two different radiations in my mind. Classical electromagnetic waves from radio waves up to X-rays and so not further. And then we have a gamma radiation. It's a totally different radiation, totally different mechanism. It's a nuclear mechanism. You
Okay.
have your electromagnetic, it's electrons, you have electrons, currents, and all this stuff.
Gamma,
You have your radiations based on electrons.
very short
Gamma
answer.
radiation, it's based on nucleus. It's totally different story.
Yes,
So
sir.
we got
Very
4
short.
minutes.
Okay, very short answer to Vladimir. What's the difference in my mind from the structured atom model perspective? The electromagnetic that we all know is on
No,
a
I
chemical,
like electromagnetic. It's a classical notion. You're right.
right.
But what about quantum physics? You see, if you're talking about square, cubic form or spherical form,
So,
I prefer spherical form. For me, as a physicist, it's much easier to take than cubic. But it's okay. Might be it's a cubic. I have no idea about this quantum physics, but I want to know something real. Annihilation, electron with positron, we have some gamma radiation. What does it mean? How it goes? What is the differences? Energy-wise, yes, huge difference in energy, but don't prescribe to gamma radiation any wavelengths because it's so short. There is no such a number in classical physics. In classical physics, there is a limit of size, 10 to the minus 14 meters. That's it. You cannot go down further. You have no size in this area of quantum physics. What does it mean, size? What does it mean,
Okay.
force? Guys, please
All
pay
right. We're
attention on
coming
the
to the end.
difference.
We're coming to the end here. We got just a few minutes. So you raised some issues. I don't, that's another topic for debate. Yes. So that's another
Yes,
issue. We can talk about that separate presentation, I think. Yes,
I would like to hear Ido next time, and maybe inside of his presentation, we will talk about all these issues. It's very
okay.
important issues.
All right, we got all right. So coming up into the end here, I'm going to give my pitch. I want to thank everybody for coming today. Jim's presentation, I think, was kind of interesting. I wasn't sure what kind of conversation or debate it would stimulate, but it certainly stimulated a lot more than I anticipated. So thank you for that. I think we have some future discussions identified, and we're kind of moving away from the topic of cosmology more to fundamental physics, which I guess shouldn't really be surprising to anybody. This issue of the structure of a proton, yeah, that's kind of it. So, Jim, I guess you're going to give a presentation to talk about your other topic that you wanted to talk about. And I don't know whether you're prepared to do that next week or not. And Ido, it'd be nice if you could give us some more discussion about the neutron. I think that's the topic that we were focused on. That would be good if you could do that.
Yeah,
So,
I could definitely present. It'll be a short presentation that the Pauli matrices actually define the cubic lattice.
yeah, okay. I'm not sure that's a topic that's going to take up 2 hours, though. Okay. All right. Okay. Does anybody have any final comments before we close out? We got less than a minute, probably 30 seconds or so. Well, thank you all. Thank you, Jim, for
Cosmology is the mother of all the sciences.
okay. Well, that ties it up. That that ties it up completely for us. Okay.